Hi everyone, my name is Matt Knight. Our team has built a machine learning model that predicts the probability of consumers defaulting on their credit cards from an unnamed Chinese bank. We are excited to have this opportunity to share our findings today. First, we will cover who our team members are, then we will move to a brief overview of our summary and findings. Afterwards, we'll go into the data acquisition and preparation, exploration, and modeling. Lastly, we'll review insights and recommendations. Anthony is going to discuss the context of our project, as well as data acquisition and wrangling. Adam is going to talk about exploration, and Bibek will cover modeling. I will conclude the presentation with insights gained and recommendations. We follow best practices in data science, using a systematic approach to guide the project from acquisition to model implementation. We use technologies including Python and Pandas, Matplotlib, Seaborn, Tableau, SciPy, IMBlearn, and scikit-learn. Here is a brief overview of our project. Our problem? A Chinese bank needs to identify customers at risk of defaulting on their credit card loans with enough time to intervene. Our goal? To develop a model that uses a customer's payment history and application data to predict loan default 6 months in the future. Our model? A logistic regression model using customers' annual income and 6 months of payment history that captures 78% of all accounts that will eventually default when tested on unseen data. Our insights? Demographic data in this data set is largely not predictive, and most demographic data should not be used to avoid unethical discrimination. And lastly, our recommended use is to flag accounts that are at risk of default for intervention and retention. At this time, I will hand it over to Anthony to further discuss the background of the project as well as data acquisition and preparation.
Thank you, Matt. In the last 5 years, the number of credit cards issued each month in China has exploded from around 450,000 in January of 2015 to around 711,000 as of September of 2020. Along with it, the amount of credit card debt has risen to 2.7 trillion US dollars, or an 87% increase since 2016. Yet, the penetration of credit cards in the Chinese market is low, especially when compared to its neighbors, as you can see on this chart with Hong Kong and Taiwan versus China. This means there's still plenty of room to grow. But with rapid growth comes risk. In this chart, we have highlighted recent periods in US, South Korean, and Hong Kong history where rapid expansion in household debt has preceded deep economic recession. There's little reason to assume the Chinese market will be any different. As such, it is of great importance for each credit card issuer to be able to predict when customers may be approaching default and intercede. In order to accomplish this, we set out to take over 430,000 credit card applications and pair them with over 1 million payment records. We accomplished this through a process we in the industry like to call data wrangling, using Python and Pandas to get the data into a format that was useful for analysis. First, we had to identify which credit card holders had at least a year's worth of payments records before defaulting. After these users were identified, we saved their first 6 months of payment history to create a blind period in order to determine if a user may default 6 months into the future. Afterwards, we grabbed the most recent year's worth of records from all the users who didn't default and ignored their most recent 6 months of records to closely mirror the defaulted accounts. Finally, we merged these users with their credit card applications to produce a single table of data where each row represented a single credit card user and each individual column represented a piece of application data, a month's worth of credit card payments, or whether or not a user defaulted. From this table, we were able to derive a user's risk score based on their 6 months of payment records, where the higher the score, the higher the risk. All this work not only allowed us to find patterns and build a model that could successfully identify a user would default 6 months into the future, but also allowed us to explore the data and gain additional insights. And with that, I'll hand it over to my colleague, Adam Gomez.
Thank you, Anthony. With the data now prepped, our next step was to do a deep dive in order to really understand who these customers were. Our application data had a lot of demographic information like gender, age, occupation, education level, and so on. With gender, we found that women outnumbered men 2-to-1. And when we compared the genders with each other, statistical testing confirmed that men were more than 2 times as likely to own a vehicle than women, while women were slightly more likely to own real estate. There were many examples beyond this, but the reason why we're focusing on this one in particular is to demonstrate the importance of really understanding your data in order to avoid unethical discrimination. For example, if we use car ownership as a means to make credit decisions, we're effectively using gender. And this should absolutely be avoided. For this reason, we focused more heavily on the payment record of our customers, and here we ran into a different kind of problem. Multicollinearity describes when two or more variables have so much in common that their predictive power overlaps with each other. We had built an array of features all based off of payment record, and so there was a lot of overlap. We used variance inflation factor to identify features that still had good predictive power, but that didn't correlate with each other too strongly, and we found 4 really good ones. Income amount represents the customer's total yearly income. And while this is demographic data, a customer's income is so closely tied to their ability to repay debt that there is a case for its use. Months with no balance represents the number of times that a customer did not have any debt with the bank. And months with balance paid represents the number of times that a customer zeroed out their debt by paying the balance in full. Total late payment score represents the degree by which a customer was late in making their payments during that 6-month window. Exploration into these factors found some surprising details. Customers who default had higher incomes, not lower. They also had fewer months where they had no debt, and there were 0 instances where they paid off their balance in full. This didn't happen once. They also had a higher total score. With these factors identified, we passed them on to our modeling phase, and Bibek will talk about that part.
Thank you, Adam. During exploration, we had identified the following factors as driving the defaults: total score, annual income, the number of times a user paid off their debt, and the number of times a user had no debt. We then used these features to build and train our model. Our data was already divided into train, validate, and test data sets. Models are trained on a train set, their results are validated with a validate set, and then the test set is used as unseen sample data to check how their performance will compare to a real-world data. But we realized we had class imbalance problem in our data. Class imbalance occurs when observations within one class are far less than the other one. In our case, the number of customers who defaulted on their loan was much smaller than those who did not. Modeling without balancing the data can lead to models favoring the majority class, which may lead to misleading predictions. So we used various under and oversampling methods such as random oversampling, random undersampling, and a synthetic minority oversampling technique to balance the classes, and then moved on to modeling. Since our goal was to identify customers who may default, we needed a model that can classify customers into either being defaulting or not defaulting classes. These types of models are called classification models. Classification models work by using independent variables to predict the class each observation falls into. In our case, the model will take information from these variables and use that information to predict whether a customer will default on their loan 6 months in the future. For this problem, we chose to run logistic regression, stochastic gradient descent, and rich classifier regression models. Don't let the name intimidate you. The end goal of all of these models is to predict whether a customer will default or not. They just have a different way of getting there. To measure these models' performance, we used recall score. Recall score is simply the percentage of correct predictions of a positive class versus the total of the actual positive class. In our case, how many customers our model said defaulted on their loan versus how many customers actually did. After training and validating, we're able to pick our top model, logistic regression model. So how does this logistic regression model work? It is a linear method, but at the core of the method, the predictions are transformed using the logistic function, also known as the sigmoid function, hence the name logistic regression. When graphed, logistic function takes a S-shaped curve that can take any real valued number and map it into a value between 0 and 1. Our logistic regression model was able to predict with a recall score of 78%, meaning if 20 customers out of 10,000 default on their loan, our model will be able to correctly identify 16 of them. Now, I'll pass it over to Matthew, who will go over insights and recommendations.
Thank you, Bibek. To summarize, after working with both application and credit history data, we found that our application data wasn't entirely useful for predicting customer default. We recommend that the bank collect different information during the application process to be more in line with global industry standards. However, we were able to create a model that considers the cost of implementation by reducing the number of flagged accounts that are not at risk of default. The next phase of continuing this project would be to obtain more information in order to determine a customer's profitability, such as the balance a customer carried and their interest rate, and use recursive feature elimination, which systematically compares the relative predictive power of each variable to optimize the features selected for modeling. If you would like to see more detail regarding our project, please refer to the alumni portal. Thank you and have a great day.